So I'm going to walk you guys through how I'm going to make some biofloc for my blackworms. I had this culture going. I took all the blackworms out of it. Now I only have the substrate and I have turned off the air. I put in a heavy dose of molasses. And another thing I did in this one, I also left the duckweed on top to start to decay because that adds fuel to what we're trying to produce here. I removed all the worms, put them in brand new substrate. And the first thing I want to do is test the nitrates. When the nitrates read 0, it is time to flip the switch. And now let's start seeding this back with the correct microbial loop that the worms depend on. And the first thing we need to do is give it some protein. The same food I would normally feed the blackworms, I'm going to feed the system without any blackworms in it. And the reason is this is exactly how you make biofloc. You have to give it a protein source, and we have to calculate it a little bit different because there's nothing in this system eating any of the food. So instead of using regular biofloc technology, we have to do it with a little twist. I know that looks super confusing, but you only have to remember one number, 1.8. Whatever the food that you are feeding weighs, times it by 1.8. That will give you the amount of molasses that you need to use in order to make the biofloc happen. So now we just toss in our pellet, add the correct amount of molasses, and just wait for the magic to happen. There's one more ingredient needed in order for this to be successful. We need to now turn on the air because we're trying to flip-flop this. We need those heterotrophic bacteria to wake back up. I'm going to make sure that the air gets all the way down to the bottom and really stirs up whatever substrate, mulm, and peat moss that's left at the bottom. Now, at this point, biofloc has started to form, but we have to make sure we check our pH. And a little pinch of baking soda normally solves the problem. But first, I want to test it to see exactly where it is before I do anything else. And this is my tester that I use. This is a professional grade pH tester. It is guaranteed to give you the correct answer. You can recalibrate it multiple times, make sure it's right before you use it. And as we see, it's 8.2. That's exactly where I need it to be. Between 7.0 and 8.5 is the perfect pH that you want for producing your biofloc. If you don't have the right alkalinity in there, it's not going to produce biofloc. It consumes a tremendous amount of alkalinity in this process. And what we're trying to make is this slime. You can see it on the air hose that is in my biofloc bucket. That's exactly what we're producing in this reaction. And that'll stick to everything and anything you put into the system. The microbes produce this sticky, crazy glue-like substance, and it will stick to anything, even the glass. This is only a couple minutes later after I added the molasses, made sure the pH was good, and turned back on the air. It's already sticking to the glass like crazy. It will stick to everything, including the substrate that's already in there. That's exactly what we want to do. We want to produce all this biofloc in the system before we even put the blackworms in it. I will be using some of the substrate that's in here to restart the experiment that we just had fail because there wasn't the correct mature microbial loop when we started the experiment. Another great addition that I'm throwing in is another product from MarinePure. This is actually a bio ball. It's the 1.5-inch bio ball. And this thing is filled with nooks and crannies and caverns for the bacteria to stick on. It'll be a smorgasbord for the blackworms. So I just plop one in, and you can see even after a couple minutes, the biofilm is already forming on them. No matter what we put in here, that biofloc is going to stick to it, no matter if it's at the bottom or floating on the top. And you can see it better here. And if you take the water and strain it out, this is what you're going to get. This is pure biofloc. This is what I'm producing in my biofloc bucket. And this is pure protein for them, about 60%. So the new substrate that the blackworms are in, I'm going to leave a little bit of the old to mix back in. And this is going to be fresh substrate in there. So it's not going to be 100% what we're making, but it'll be a perfect condition for the worms to start out in. The correct microbial loop to protect them, the right microbial loop to allow them to eat. And we should have a more successful culture without anything really happening. This should be the majority of the substrate they will live in. And I know this sounds really confusing to a lot of people. And I had my new notebook app make a new video trying to explain biofloc a little better in the process that happens. Hopefully this will help you understand a little bit better, and you'll see why it's pretty perfect for blackworms.
Welcome to the Explainer. Today, we are uncovering what I can only describe as a literal biological cheat code. We're going to completely demystify the somewhat complex ecological mechanics of the nitrogen cycle. We're looking at a system that takes what we traditionally consider toxic waste and transforms it into an endless engine of growth.
So here is the big question for us today. How do you build a biological machine with absolutely zero waste? Sounds kind of like science fiction, right? Well, what if I told you that by manipulating just a few key variables, we can essentially override nature's standard operating procedures? We can actually engineer an infinite, self-sustaining loop that feeds itself, cleans itself, and leaves absolutely nothing behind.
Section 1. The Aquatic Waste Problem, and enter biofloc technology.
All right, let's dive right in by looking at the biggest roadblock in literally any aquatic farming system: toxic ammonia. You see, anytime you're culturing aquatic animals, and for us today we're talking about the freshwater blackworm, you gotta feed them. But here's the catch. High-protein feeds inevitably cause these organisms to excrete ammonia. And in a closed system, that ammonia is incredibly toxic. Traditionally, the only way to solve this ammonia roadblock was to do massive, constant water changes. You're basically flushing the poison down the drain, but you're taking tons of perfectly good water with it. It's wasteful, and it's just terribly inefficient.
To really understand the fix, we gotta look back a few decades, to the origins of biofloc technology, or BFT. The very first biofloc systems actually popped up back in the 1970s at IFREMER COP. That's the French Research Institute for Exploitation of the Sea. Fast forward to the 1980s, and research and development really started to expand in Israel. By the 1990s, BFT was being actively used in the USA to farm shrimp and tilapia. The big realization here? They figured out they didn't need to throw the water away. They just needed to change the biology within it.
So, what does this technology actually do? Simply put, BFT is a system that intentionally manipulates the carbon-to-nitrogen ratio in the water. See, when you've got high nitrogen from all that ammonia, the heterotrophic bacteria, the microbes that eat organic matter, are usually just starving for carbon. If you step in and give them a carbon source, these bacteria multiply like crazy, slurping up all that toxic ammonia and converting it straight into microbial biomass. It is literal biological alchemy. We are turning a toxic problem directly into a high-protein food source.
Applying this requires a massive paradigm shift in how these systems operate. Blackworms actually have two distinct ways to feed. You can feed them directly, which, as we just saw, causes a totally toxic imbalance, or you can feed the microbes and let the microbes feed the worms. We really have to completely rethink the way we look at blackworms. We aren't just farming worms here, we are managing a complex aquatic compost ecosystem that just so happens to produce blackworms as a byproduct.
The absolute foundation of this ecosystem is something called mulm. Basically, mulm is a mature biological layer of living sediment. Think of it as a slow-release food source. Instead of just dumping raw food into the water and causing these massive rapid ammonia spikes, the mulm gradually feeds that microbial layer over time. It maintains a really stable oxygen demand and gives continuous controlled feeding for the whole system, completely preventing it from getting overwhelmed.
This brings us to how we actually control that bacterial engine. I like to think of it as the molasses volume knob. Molasses is our chosen carbon source here. In a normal, oxygen-rich environment, we microdose, meaning we add just a few drops of molasses alongside the high-protein food. That provides just enough carbon to instantly convert toxic ammonia into protein. But if we want to radically flip the system's behavior, we macrodose. We pour incredibly heavy doses of carbon into an oxygen-deprived environment. This intentionally overwhelms the system and forces the bacteria to overproduce a thick, highly nutritious slime.
Section 2. The stagnant reset phase, and triggering total denitrification.
Let's move on to our next major roadblock and see how this all flips to an entirely opposite biological spectrum. We've mastered the aerobic, oxygen-rich creation phase, but what happens when you run that engine a bit too long? Well, you hit a plot twist, the nitrate problem. The aerobic biofloc engine works amazingly well at removing ammonia and nitrites, but at the very end of that process, it leaves behind a buildup of nitrates. While they aren't as toxic as ammonia, excessive nitrates will eventually slow down the growth of your organisms. In standard aquaculture, this is exactly the point where farmers just throw their hands up in defeat and go back to dumping and discharging that water. But we are not going to do that. No way! Instead, we initiate what we call the stagnant reset phase. Step 1. You completely shut off the water flow and aeration. Zero movement. Step 2. You macrodose a heavy amount of carbon using molasses. Step 3, because there is absolutely zero oxygen in the water now, these desperate anaerobic bacteria are forced to literally strip the oxygen molecules right off the accumulated nitrates just to survive. And then, step 4, the magic happens. Those nitrates are converted into completely harmless nitrogen gas, which just bubbles up and escapes into the atmosphere. Total denitrification. The water is scrubbed completely clean.
Now you might be wondering, if there is absolutely zero oxygen in the water during this stagnant phase, how on earth do the blackworms survive? It's a pretty incredible biological quirk, honestly. Blackworms possess a unique adaptation, allowing them to survive in severely anoxic environments that would instantly wipe out other organisms. When the oxygen plummets, the worms are biologically forced to migrate straight up to the water's surface. They intertwine with each other on floating mesh, and they just breathe directly from the atmosphere right through their skin.
And this forced migration gives us a brilliant secondary benefit. It is the ultimate self-harvesting hack. Normally, to harvest worms, you dump the whole culture through a net and violently wash away all the mud. But doing that completely destroys the precious Mulm biofilter you spent so much time cultivating. By deliberately triggering this oxygen-deprived, stagnant phase, the worms literally do all the work for you. They evacuate the mud entirely and gather tightly on a floating mesh at the surface. You just lift the mesh out, and boom, you have 100% perfectly clean worms, totally bypassing the need to destroy your delicate biological processing layer.
While they are hanging out up there at the surface, we take full advantage of the bulking up phase. Because we macrodose the whole system with carbon earlier, the bacteria are producing massive amounts of floating biofloc slime. And get this, that slime is roughly 60% crude protein. The worms just rest stationary on the mesh for an extra week. They're expending zero energy burrowing or searching for food. They literally just sit there gorging on this floating microbial biomass, converting pure bacterial protein directly into immense weight and thickness.
Section 3. The infinite zero-waste loop. So, the absolute key takeaway here is how we synthesize these two opposing phases, aerobic creation and anaerobic destruction, to hit total sustainability. Honestly, to run this loop, we have to throw out some textbook rules. First up, contrary to a lot of old literature, blackworms actually love light. Constant bright light drives photosynthesis, which creates this amazing solar buffet of microalgae for them to graze on. Second, we have the anti-lockbox rule. You'd think a heavy bioflux system would turn the mud into a solid compacted brick, right? Well, the dense population of worms acts as tiny little plows, a process called bioturbation, constantly churning the substrate and keeping it oxygenated. Finally, we have to solve substrate exhaustion. Instead of throwing away old broken down dirt, we recycle it. Which brings us to the multi-stage recharge bucket. This is exactly how we recycle that dead dirt. When that biological processing layer looks totally exhausted, we don't just toss it. No, we throw it into a recharge bucket with heavy aeration and molasses. The heterotrophic bacteria go to work scrubbing the waste, breaking down the exhausted sludge, and converting those leftover toxic metabolites right back into edible microbial protein. We are literally recycling waste back into high-protein worm food. That means this biological sediment can be reused indefinitely. Which leaves us with this final, stunning realization. We use aerobic biofloc to magically turn toxic ammonia into protein to feed our culture. Then, we just flip the switch to an anaerobic stagnant phase to seamlessly gas off the leftover nitrates and cleanly self-harvest the culture, all without destroying our ecosystem. By perfectly toggling back and forth between aerobic creation and anaerobic destruction, haven't we just programmed nature's ultimate zero-waste infinite loop? It fundamentally changes how we interact with ecological mechanics. And honestly, it's a brilliant, exciting glimpse into the true future of sustainable biology.
I hope that helped explain it just a little bit more and why this system is the perfect combination for blackworms.